We learnt about Nd:YAG lasers and carbon dioxide lasers in previous segments. In this last and final segment of this chapter, we will be learning about the third important kind of lasers, semiconductor lasers. So as the name suggests, the active medium is going to be a semiconductor, particularly a direct band gap semiconductor. Direct band gap and indirect band gap is a concept we looked at when we were studying about semiconductors. Just to quickly refresh your memory, the minimum energy level at the conduction band and the maximum energy level in the valence band both occur at the same momentum. So when an electron from the valence band is going into the conduction band, for example, it simply moves directly from this energy level to that energy level. It does not spend time searching for an energy level with the same momentum. So maximum recombination happens and very fast. So that is a direct band gap semiconductor. So what we need to know about them in the context of semiconductor lasers is that the active medium in an SC laser is always a direct band gap semiconductor. The pumping mechanism is injection current induced luminescence. So if you remember from classification of lasers based on pumping mechanism, we had optical, electrical, chemical, and the fourth was something called injection current or current injection. So that is what is the pumping mechanism here. So what exactly is this about? When you have a PN junction, the P region and the N region, remember P region generally has a lot of holes, N region has a lot of electrons, and when you provide forward biased current, electrons from the N type move into the P type, holes from the P type move into the N type. The junction region, the junction of P and N, where they cross over, you have both a large number of electrons as well as a large number of holes. And in this location, radiative recombination of electrons in the conduction band with holes in the valence band happens. So this is basics of semiconductor. So P region is rich in holes, N region is rich in electrons. You provide forward biased current, they both start combining, that is electrons move from N to P, holes start moving from P to N. In the center, the junction region, the concentration of both these entities are high. So the electrons start combining with the holes. When this recombination happens, a photon is given out. So this is also something we studied when we were looking at quantum, if I'm not wrong, but we learned this point that when recombination happens, a photon is given out. So even if you don't remember it from quantum, I need you to understand this now. When a hole and electron combine in the junction region, they need to invest some energy in order to combine, and that energy is given out in the form of a photon. And once a photon is released, you know the rest of the story. So that photon triggers stimulated emission. Stimulated emission happens and then repeated amplification and laser light is produced. So all that is the usual stuff. So the only question is, so whenever you're studying about a particular laser, one part of the working mechanism is constant. A photon is released first because of some process. That photon triggers stimulated emission, then stimulated emission happens, then repeated amplification, gain per pass equals loss per pass, and the rest of the story is the same. The only differences between Nd:YAG and CO2 and semiconductor lasers and any other type of laser you look at will be, one, what is the pumping mechanism, and two, what exactly triggers or leads to the emission of that first photon, the photon which triggers everything else. So that those 2 points are the only things which will differ from one type of laser to another. So here the pumping mechanism is current injection, meaning you provide current in terms of forward bias, and what exactly gives birth to that first photon is the recombination of electrons and holes in the junction region. So once that first photon is out, then normal stimulated emission and so on and so forth. So here is a sort of diagrammatic representation of the same thing. Generally, you take a normal P region of a semiconductor. This is the valence band, conduction band. Fermi level lies closer to the valence band. Valence band is filled with holes. If you take the N region, again valence band, conduction band. Fermi level is closer to the conduction band, and conduction band is filled with electrons. These are things you know from your semiconductors chapter. Now, this is a PN junction diode where you have a P region and N region, and this central part is the junction region. So normally your this is your p region holes, n region electrons. This is the energy of the conduction band, this is the energy of the valence band, and this red line in between is the Fermi level. So if you can see, in the p region the Fermi level is closer to your holes or to your valence band. At the n region it is closer to the conduction band, but it is still just one Fermi level. This is normally when you have p and an n, you have not yet provided current. Now when you start providing current forward bias, the Fermi level splits into two because of these photons which are being generated. These photons are the spontaneously emitted photons because of the recombination. These will now trigger stimulated emission and light production will happen, but these are the initial photons. So now in the p region the Fermi level slightly decreases and remains closer to the valence band. In the n region it slightly increases and it becomes closer to the conduction band. So the Fermi level is no longer the same for p region and n region, there is a split. And as that split happens, we also need to note that electrons are moving from n region into the junction region, holes from the p region into the junction region. Recombination occurs and photons are released. This is the carrier concentration. P region high on holes, low on electrons, n region vice versa, junction region moderately high quantities of both. So yeah, the reduced voltage allows electrons to flow from n to p and holes from p to n respectively, leading to radiative recombination. The diffusion of electrons is governed by the diffusion length. So the length of the junction region plays an important role in how much recombination takes place, because the longer it is going to be, the more electrons and holes will be there, so the more recombination can take place. So that is that. Again, a quick overview of the same process. When current is injected, photons are generated through stimulated emission seeded by the initial spontaneously emitted photon. Initially there is a spontaneously emitted photon because of your recombination that triggers stimulated emission. These photons in turn stimulate more photons. So stimulated emission photons, like we already know, they trigger more stimulated emissions. The cleaved faces of the semiconductor themselves act like the mirrors. So you don't need a separate setup here for repeated amplification. The faces, so if this is the length, then this face and the corresponding opposite face of the semiconductor themselves will act like the mirrors, reflecting back. Again, they undergo further amplification for each pass. This you know. Stable emission when gain per pass is equal to loss per pass. This again you should be familiar. The minimum current required to achieve this is called threshold current. So like I said, this mechanism remains the same. The only changes are the pumping mechanism and what gives rise to the first spontaneous photon. So that we have seen. So one last topic here is threshold current. So you know threshold population inversion, and population inversion happens because of a pumping mechanism. And the pumping mechanism in case of a semiconductor laser is current. So wait, what is threshold population inversion? First of all, the minimum population inversion required for stable laser action. And population inversion happens as I continue to provide current. So how much current do I provide to achieve threshold population inversion? That is called by threshold current. So the minimum current required to achieve threshold population inversion is called the threshold current. So we will look at a graph to understand this. You start providing current. Initially there is only spontaneous emission. The recombination happens of electrons and holes in the junction region. Because of that, photons are given out. That is only happening as you keep providing current. This is the amount of current on the x-axis and the output power in the y-axis. So as long as spontaneous emission is happening, you don't have much power. You don't even have any light emission actually. Almost close to nothing, because you need stimulated emission for lasers. So once it crosses the threshold value, stimulated emission begins, so your power increases. So that's the green line. The blue and red lines represent the same thing at lower and higher temperatures. So what this graph tells us is, as your temperature increases, your threshold current is going to increase. Why does that happen? So if your temperature is rising, it means more energy is being given. So intuitively it would seem like the threshold current should decrease, right? But here it says it increases. Why so? Because as your temperature rises, non-radiative recombination is going to increase. What is non-radiative recombination? There is going to be recombination of holes and electrons in the junction region without giving out a photon. The energy might be given out in form of heat or something else, but it is not in the form of light. And if it is not a photon, it is not going to help you in triggering stimulated emission. Laser light will not be produced. So as your temperature rises, you have to increase the threshold current to make sure radiative recombination still happens, and hence light is still produced, laser light is still produced. Yeah, so this is a graph of wavelength versus intensity. In spontaneous emission, you can see the intensity is very less and the wavelength of light emitted is spread over a large region. So some amount of light will be emitted even during spontaneous emission because photons are still coming out, but the intensity is very poor and the wavelength is spread over a large region. So it is neither intense nor monochromatic, if you remember the properties of a laser. Whereas this is for stimulated emission, highly intense, and wavelength is also a very narrow spectrum, meaning it's highly monochromatic. These are things you know. Now, homojunction laser diodes. So what are homojunction laser diodes is? Homo means one or the same, and junction is just the PN junction. So it means you have one P type region and one N type region and just one junction. So if it's gallium arsenide, you just have the P type of gallium arsenide, the N type of gallium arsenide, that's all. So you have only one semiconductor. So that is the normal semiconductor laser setup. The problem with these are you need to provide high threshold currents and you will still get only low output powers. Why? Because you do not have optical confinement or carrier confinement. What are these two? Optical confinement. So photons are being generated, right, by whatever emission process. So these photons, they might get refracted and move out of the semiconductor itself and travel into air, for example. So this is like your fiber optic cable, the signal traveling out of the cladding and into air, loss we saw, right, especially when the cable is bent or something. So if let's say this is your setup and your photons are generated somewhere here, if it's a homojunction, this is a homojunction by the way, first of all, you have one P type and one N type. So generally they do not have optical confinement, meaning the photons, they easily refract and go out of this surface. So as long as they remain along this horizontal axis, this surface and the corresponding opposite surface will act as mirrors, reflecting back and forth. But what if they travel out through this upper or lower face or through this left or right face? That possibility is high in a homojunction diode. So optical confinement, the optical as in the photons, are not confined. Secondly, carrier confinement. Carrier confinement is the P type and N type charge carriers, that is the holes and electrons. They are also not confined or held together very strongly in the junction region. The electrons, for example, can escape and get leaked out. So the problem with homojunction semiconductor lasers is, meaning semiconductor lasers where you have only one semiconductor, is both the photons as well as the electrons have a chance of leaking and getting out of the system. So you have to provide a large amount of current for pumping. You will still get only a low output power. So that is inefficient, right? So we come up with something called the heterojunction lasers, which we will be looking at now.